In question 1, part A, to take the derivative of the function f of x, I'm noticing that there is a composition of two functions, and so I'll note that we must use the chain rule. And also here, there's a fraction, so we'll have to use the quotient rule. And one last final thought, I'm noticing here and here, those are compositions as well, meaning you have to use the chain rule on e to the negative x. So I'll note off to the side that when you have to take the derivative of e to the negative x, you get e to the negative x, but by the chain rule, you get -1. So here we have to use the chain rule as well. Let's put all of these ideas together to find f prime of x. Okay, first we take the derivative of cosine, which is minus sine, and we leave the inside part alone, like this. To complete the quotient rule, we have to multiply by the derivative of the inside using the quotient rule that is the denominator, which is 1 plus e to the minus x, times the derivative of the numerator. The derivative of the numerator is, well, 1 goes to 0. We have minus e to the minus x times -1. So that's minus e to the minus x multiplied by -1. Okay, to complete the quotient rule, you subtract. Now it's the numerator times the derivative of the denominator, which is, that goes to 0. We have plus e to the minus x, again, times -1. And this is all divided by the denominator, which is 1 plus e to the minus x squared. And this is unsimplified, but this is the derivative. In part B, to take the derivative of g of x, here we have a product, so we must use the product rule. And here we have a composition, so we're going to use the chain rule. To take the derivative of g, okay, the product rule says it's the derivative of the first, which is just e to the x, and then you copy down the second. Now we add on, we leave the first alone and take the derivative of the second. Off to the side, I'll note that, well, the square root of x is x to the 1/2. So when it comes to taking the derivative of the square root of x, you bring down the 1/2, copy down the x, subtract 1 from the exponent, and that's it. Now we add on the derivative of the natural log of tangent of x. The derivative of the natural log is 1 over, and here we have tangent composed in place of it. By the chain rule, we have to multiply by the derivative of the inside part, tangent, which is secant squared of x. And unsimplified, this is the derivative g prime of x. In part C, to take the derivative of h, here we have two compositions. So because of the compositions, we actually have to use the chain rule on both parts. And before taking the derivative, I'll note that instead of the square root of x, I'm really thinking x to the 1/2 power. So to take the derivative of h prime of x, this is equal to the derivative of arcsine, which is sine inverse. That's 1 over the square root of 1 minus whatever's in place of it squared, and 2x is in place of it. By the chain rule, you have to multiply by the derivative of what's composed in this function. The derivative of 2x is just 2, and I'll put that here. I now add on, okay, here we have to take the derivative of secant. The derivative of secant is secant times tangent, both with the square root of x in place of it. So it goes to secant root x times tangent of root x. However, by the chain rule to complete this problem, I now have to multiply by the derivative of this thing, which I'll look to here to do that. I bring down the 1/2, copy down the x, and subtract 1 from the exponent, and this is the derivative of h. To take the derivative of y is equal to x to the 3 cosine of x, I'm going to use logarithmic differentiation. And the reason for this is because I have a variable in both the base and within the exponent. So to start with, I'll write down y is equal to x to the 3 cosine of x. And the first step is to take the natural log of both sides. And the reason for this is there's a property of logarithms that says we can take this entire exponent and write it here, changing this into a product. We have the natural log of y is equal to 3 cosine of x times the natural log of x. Again, this whole thing I wrote in front of log x. To differentiate this, we need to use implicit differentiation because this side isn't just y, it's the natural log of y. So the derivative of this with respect to x is, it's 1 over y, but by the chain rule, we have to multiply by the derivative of this thing with respect to x. Well, that's just dy dx. You could also use the symbol y prime. On the other side, when we differentiate with respect to x, we have to use the product rule. Now that says we take the derivative of the first, which is minus 3 sine x, and we multiply it by the second. We then add on, we leave the first alone, and then take the derivative of the second, which is 1 over x. The ultimate goal is to solve this for dy dx, and over here, I want to express the function as something just in terms of x. What I can do is take this y and multiply to the other side of the equation, and the derivative is all by itself. So I have dy dx is equal to y times, this is minus 3 sine x natural log of x. And I'll put this next piece as a single fraction. I'll say this is 3 cosine x over x. So there are no derivatives over here. The derivative is only on this side, the thing we wanted to solve for. But this is y, and I think we can express this in terms of x. This relationship is always true, so I'm going to replace y with x to the 3 cosine x. So the final answer, dy dx, is equal to x to the 3 cosine x, all times minus 3 sine x natural log x plus 3 cosine x all over x, and this is the answer. Let's find dy dx for this implicitly defined function. Step number 1 is to take the equation, which is e to the y cosine x equals 100 plus sine xy squared, and I take the derivative with respect to x on both sides. On the left side, I have to use the product rule. So here's my first term and here's my second. To take the derivative of the first, I have to write that as e to the y. And since this is a y and not an x, I have to multiply by its derivative, which we can express as either y prime or I'll put dy dx. And then we copy down the second. To this, I add the first, I leave it alone, but I multiply by the derivative of the second, which is minus sine of x. Now, on the other side of the equation, if I differentiate this side, I can first differentiate the 100, which will give me 0, plus, okay, here I have to use the chain rule. We have a composition of two functions. Dealing with the outside part first, the derivative of sine is cosine, and I leave the inside part alone. But by the chain rule, I have to multiply by the derivative of the inside, which is a product. Using the product rule, I'll take the derivative of the first, which is 1, and I'll copy down the y squared. To that, I add the first times the derivative of the second, which is 2y, but you get dy dx. So that is, you bring down the 2, copy down the y, subtract 1 from the exponent, but by the chain rule, you'll have to multiply by the derivative of y, which is dy dx. Let's clean this up a little bit. Let's see. I'm going to write this term as e to the y cosine x, and I'll put this last. So this is, maybe I'll put this cosine x e to the y dy dx. And this I'll write as negative sine x e to the y. And on the other side of the equation, I'm going to distribute this into the parentheses. When I don't need to write this 0. When I multiply this here, I'll put y squared cosine xy squared. And then when I multiply this here, I'll put 2xy cosine xy squared and then the derivative. So that's 2xy cosine xy squared and its derivative, dy dx. The trick for finding dy dx, isolating it, we're going to put everything with a dy dx on, let's say, the left side of this equation, and everything that doesn't on the other side. So essentially, I'm going to subtract this here, and I'm going to add this here. I'm going to do that all in a single step. So we get cosine x e to the y dy dx minus 2xy cosine xy squared dy dx is equal to y squared cosine xy squared plus sine x e to the y. The reason this will help us is we can factor out dy dx from both terms on the left. We can then divide whatever is remaining to the other side of the equation, essentially solving for dy dx. So we have dy dx times cosine x e to the y minus 2xy cosine xy squared is equal to y squared cosine xy squared plus sine x e to the y. I will now divide this to the other side of the equation, leaving me with my final answer. So what does dy dx equal? It equals this divided by this. That is y squared cosine xy squared plus sine x e to the y, all divided by cosine x e to the y minus 2xy cosine xy squared. So this gigantic final answer is it. In question 3, part A, we want to find the points on the curve here where the tangent line is horizontal. When does this happen? When do you have a horizontal tangent line? That's when the slope is equal to 0, or more specifically, where the derivative of y with respect to x is defined and equal to 0. So I'll take this equation y and find dy dx, or y prime. When we do that, we get 6x squared plus 6x minus 12. Any place where this derivative is defined and equal to 0, there must be a horizontal tangent line on the graph. So basically, we need to solve this problem here. When does this happen? Okay, I see I can factor a 6 out from every single term. And does this factor, it's a quadratic, it might have two real solutions. Okay, x and an x. I'm thinking a positive 2 and a negative 1, and that seems to work. Product goes to negative 2, the sum is going to be positive 1. This means there are two real solutions to this quadratic equation. That's where x plus 2 is equal to 0 and x minus 1 is equal to 0. So that is at negative 2 and also positive 1. So those are the x values where on this graph there should be some type of horizontal tangent. It asks for the points. So for x is equal to negative 2, we should figure out what the corresponding y value is. So that is equal to, let's see, that's 2 negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2 plus 3. Okay, negative 8, negative 16. Write that down. So we got negative 16. All right, then that's going to be positive 4 and 3, that's 12. That's going to be a positive 24 and also a positive 3. Okay, negative 16 and a positive 12 is negative 4, which drops this down to a negative 1. So 23, okay. 23 is the corresponding y value. So that means one of our points is the point x is equal to -2 and y is equal to 23. We also have x is equal to 1, and the corresponding y value is, okay, let's see, that should be easier. 2 times 1 cubed plus 3 times 1 squared minus 12 times 1 plus 3. All right, so that's 2 plus 3 minus 12 plus 3. All right, so 6, 7, 8 minus 12 is -4. And this is our other point. When x is equal to 1, y is equal to -4. And at these 2 points on the graph, there should be a horizontal tangent. All right, so in part B, if a ball is thrown upward with a velocity of 80 feet per second, then its height after t seconds is given by this equation. What is the maximum height reached by the ball? Since the equation s tells you a distance, if you take the derivative of this equation, s prime of t, this will tell you the velocity of the ball. So if we think about how this ball travels, it starts here. So this is where it will start. And then it's thrown upward. The velocity slows down, and eventually it'll stop. And the place where it stops is going to be the maximum height. And stopping means the velocity is equal to 0. So what we need to do for this problem is take the derivative of this equation to get the velocity, and then solve it to figure out where the velocity is actually equal to 0. And that means we must be at the maximum height. So let's see. V of t is equal to s prime of t, which is 80 minus 32t. So the velocity v of t is equal to 0 when 80 minus 32t is equal to 0. And so that's when negative 32t is equal to negative 80, or when t is equal to negative 80 over negative 32. The negatives cancel, and this simplifies to, all right, so 8 goes into both of those. That's 10 over 4, or 5 halves, and that is seconds. So to reiterate, the maximum height is achieved when the velocity v of t is equal to 0. And this happens at 5 halves seconds. Now, what is the maximum height? We now take this time, 5 halves, and we put it into the function s of t. And when we evaluate this, we'll have some distance in feet, which is the max height. So I'll say the max height is s of 5 halves, which is 80 times 5 halves minus 16 times 5 halves squared, whatever that simplifies to. And this will be in feet. Okay, so, all right, 2 goes into 80, that's 40 times 5, this is 200. When you square this, you get a 4, and 4 goes into 16 4 times, and that's going to be 4 times 5 squared, which is 25. So this was 200. This is really 4 times 25, which is 100. And so this actually simplifies to 100 feet, and this is the maximum height. In question 4, part A, we are told a bacteria culture initially contains 100 cells and grows at a rate proportional to its size. So first, this language, grows at a rate proportional to its size, means if P represents the population, the rate at which the population grows is a constant times the size of the population. So growing proportional to its size. And this differential equation has a solution, P, which is equal to P naught times e to the k t. And you could actually also represent this as P naught times some base b to the power of t. You can actually use either of these equations. This solves this differential equation. So we want to find the number of bacteria after 2 hours. This means we have to find an equation, meaning find P naught and K, and then we'll put the number 2 into that equation to get our answer. So for starters, P naught is the initial value, and that's this number here. We're told we're starting with 100 cells. So for this reason, P naught is equal to 100. And I'll use this version of the equation. That is, P is equal to 100 times e to the k t. To complete the equation, I need to find k. And we are told that after an hour, that is when t is equal to 1, the population equals 320. So within this equation, we're told that if you put 1 hour in place of t, the answer you get back is 320. We can enter this information into this equation, leaving k as the only unknown which we can solve for. That is, if p is equal to 320, then t is equal to 1, and this equation becomes this. A 1 in place of t I won't write. To solve for k, I'm going to divide both sides by 100, which yields 3.2 is equal to e to the k. And here I'm going to take the natural log of both sides. The reason being, the natural log and e are inverses, and this cancels to just k. And that means k is the same thing as the natural log of 3.1. Sorry, 3.2. I know P naught, I know K. I now have a complete equation. P is equal to 100 times e to the natural log of 3.2 times t. To now use this equation to figure out the number of bacteria after 2 hours, I can put 2 in place of t and simplify this down to figure out P of t. So that is P of 2 is 100 times e to the natural log of 3.2 times 2. Now, whatever number this is the number of cells of bacteria. Without a calculator, I'm not exactly sure what that number would be, so I'm just going to leave the answer as that. I'm going to leave the answer as 100 e to the natural log of 3.2 times 2. So this is the bacteria after 2 hours. Note that the direction says your answer may involve logarithms and the number e, and that happens here. We have e in the natural log. I will note that you can also write this equation as 100 with a base of 3.2 to the power of t. And the reason is e to the natural log here is the same thing as just 3.2. So as an alternate answer, you could say the formula P is equal to 100 times 3.2 to the power of t. Again, this 3.2 is equivalent to this, so I can replace this with simply 3.2 to this power. Here, to figure out P at 2, that is equal to 100 times 3.2 squared. And this would be cells of bacteria after 2 hours. If you square 3.2, I think that's, let's see, it's going to be 10.24. And if you multiply that by 100, P of 2 is actually equal to 1,024. And this would be cells of bacteria at 2 hours. And this would be an acceptable answer too. It really depends on which form of the equation you choose to use. So you could either write your answer as this, if you used this version of the equation, or if you wanted to simplify it, you could write it like this, if you're using this version of your equation. In part B, we are told a cylindrical tank with radius 8 meters is being filled with water at a rate of 4 cubic meters per minute. Can we use this to figure out how fast the height of the water is increasing? I'm going to draw this cylindrical tank. So cylindrical tank means the top is a circle, and I'll give it a height like this. And we are told the radius is fixed and it's 8 meters. So that's the distance from the center out to here. This is always 8. Now, water is being poured in, so we have water in, and therefore the water level in the tank is rising. So I'm actually going to draw a height h in here. And as water goes in, the water level is increasing according to this height. What we need is a formula that connects the volume to the height and the radius. And that formula is V is equal to pi r squared times h. And this formula is saying you take the area of this circle and you multiply by the height, and therefore you get the volume. Now the height is the height of the water. So it could, be here, it could be here. What I really care about is how fast is h increasing. In terms of our given information, we know that dV dt is equal to positive 4 cubic meters per minute. Positive because the volume is increasing and the number associated with it is 4. We are also told that r is equal to 8. That is this radius here. That never changes. And the thing that we're looking for is how fast the height, the water level, is increasing, which is dh dt. That is the thing I do not know. I'm going to put 8 in place of r. So this equation becomes V is equal to pi 8 squared times h. And that is volume is equal to 64 pi h. To figure out this rate, by knowing this one, I'm going to take the derivative with respect to t of this equation here. So I'm taking my equation, V is equal to 64 pi h, and I'm differentiating both sides with respect to time. On the left, we simply get dV dt. On the right, we get, well, this is a constant, so I'll ignore it for now, and we have h. The derivative of h with respect to t is simply dh dt, and then we multiply this constant back. So we get 64 pi dh dt. So if you know this rate, then you can use it to find this rate. I will do that work over here. I'll put 4 in place of dV dt. This is equal to 64 pi times dh dt. To get dh dt by itself, I'll divide both sides by 64 pi. And I can simplify this. dh dt is equal to, okay, if I cancel a factor of 4, I believe that's 16. So I get 1 over 16 pi, and the units on this would have to be meters per minute. Meters and not meters cubed because we're talking about a distance, so a distance is going to be just in meters, and the unit of time in the question was in fact minutes. So how fast is the water increasing? This fast. This is how fast the height of the water increases. In question 5, part A, we want to use a linear approximation or a differential to estimate e to the 0.02. So the way this works is we want to use a function L of x, which is a linear approximation to a given function. And the formula for L of x is going to be f prime of a times x minus a plus f of a. So in order to use this formula to find a linear approximation or a linearization, we have to have some function that we're starting with. So for this question, there's no given function that is stated, but hopefully based on this expression here, we can come up with a function as well as a number a to find this approximation for. I think the most obvious choice would be, well, I'm going to use e to the x. And the number for a would have to be something close to this number here. And I think the most obvious choice for that is a is equal to 0. So with these choices, I'm going to find this linearization, which is also called a linear approximation, and then I will use that to estimate this value here. So to use this formula, I need to know a, which I do. It's 0. 0 is the integer that's closest to 0.02. I need to know f of a. I can figure that out because I have a function f of x. And then I have to find f prime of a, meaning I have to take the derivative of this thing and evaluate it at this number. We can do all of those things. To start with, what is f of 0? That's e to the 0, and that's 1. I need to know f prime of 0, so I first need to know f prime of x, and that's just e to the x. And f prime of 0 is e to the 0, which is also 1. Here is the linearization. It's equal to f prime of 0, which is 1, times x minus 0, plus f of 0, which is 1. This simplifies very nicely to just x plus 1. What does this all mean? It means that our function, f of x, which is e to the x, is really close to the linear function x plus 1 as long as x is near a, which we chose to be 0. So these two functions are very close to each other as long as you're very close to 0. And thankfully, 0.02 is very close to 0. So if you want to figure out e to the 0.02, that's the ultimate goal of this problem. You want to know e to the 0.02. Well, that's equal to f of 0.02 based on the way we defined our function. If you put 0.02 here, you're putting it here. But since this number is near 0, I can actually put it here and it will be a very good approximation. That is, this is approximately 0.02 plus 1 if you put this number into x. And 0.02 plus 1 is 1.02. And this means e to the 0.02 is approximately equal to 1.02. And this is our estimate by using this linearization, or what we call a linear approximation. In part B, I want to compute delta y and dy for this given function. Delta y tells you how the y values of the function itself are changing over some distance for x. And dy asks the question of how's the derivative changing over this distance for x. Let's start with delta y. To help visualize what I'm looking for, I'm going to draw a very basic sketch of the square root of x. So I'll put that here. So the square root of x is a function that looks like this. And we're saying we're starting at x is equal to 1, and we're going a distance away from this 0.1. So that means here we're at 1.1. And the distance from here to here is what we call delta x, which is 0.1. So if you start here at this y value and you go over 0.1, the distance the y value increases is what we call delta y. So basically, we are given this distance of 0.1. We know this, and our job is to figure out this distance, and this is delta y. So delta y is very simple to compute. It's going to be the difference of the y value here and the difference of the y value here. So that is delta y is y2 minus y1, where y2 is this number, so I'll call this y2, and then y1 is this number, which I'll call y1. What is y2? We have the function. It's very easy to compute. You can put 1.1 in place of x, and it tells you this value up here. So y2 is equal to the square root of 1.1. I don't know what that is exactly because I don't have a calculator, but then we subtract the y value here at 1, and that is the square root of 1, which I actually do know that exactly. It's equal to 1. But here, delta y, the exact value, is the square root of 1.1 minus 1. I won't simplify it, but it is exactly equal to this. Again, just to reiterate, when you solve for delta y, you want to know the change in the y values over the change in some given x values on a given function. And this can be done by simply subtracting two y values. Now, dy is a differential, and it's asking a different question. It's not asking how the y values of the original function are changing. Instead, it's asking how the derivative is changing over this same distance. So if you try to visualize this, you would draw a tangent line like this and ask, well, not how are the y values changing on the original function, but how are they changing on the derivative from the starting point? To simply compute it, if y is equal to the square root of x, to solve for dy, you would take the derivative of this and then multiply by dx. What is the derivative of the square root of x? It is 1/2 x to the negative 1/2. And the only difference here is I'll put a dx at the end. If you want to solve for dy, you can take the derivative of your equation as you normally would, but the dx is multiplied to the other side. We have all the given information we need to compute dy. We're told that x is equal to 1, and we're also told that dx is equal to 0.1. So I'll note that too. So here, we have that x is given as 1, and dx is given as 0.1. Putting that information into the equation, we get 1/2, 1 to the negative 1/2 times 0.1, which is 1/2 times 0.1, and half of 0.1 is 0.05. We have our answer that dy is equal to 0.05. And that is the exact answer for the differential of y. In case if you're all curious, visually, delta y should be less than dy, just because if you draw the tangent line, clearly the y values on the tangent line are a little bit more than that on the original function itself. I typed this number into my calculator, and I got 0.0488, which is a little bit less than this number here. So if you compute it that way by checking your numbers on a calculator, these do seem to make sense. In question 6, we're told the half-life of cesium-137 is 30 years. Suppose we have a 40 milligram sample. After how many years will only 1 milligram remain? Since we are talking about half-life, we can use the formula P is equal to P naught e to the kt to represent the amount of cesium-137 at any moment in time. And the reason for this is when you have decay in this form, the rate of decay, dp dt, is proportional to the amount of substance that there is. So since this condition is met, since we are talking about half-life, we can use this formula to model how this thing decays over time. What we need to figure out is, well, what is the initial amount? That is this given information here. It is 40 milligrams. I'll just say 40. And we put this into the formula, we get P is equal to 40 e to the kt. To complete this formula, we need to solve for k. Now, how do we find that? We need to know a point on this equation, and we can use the half-life to figure that out. By that I mean, if you were to put 30 in place of t, what amount or how much of this stuff would you expect to have left over? It should be half of what you started with, which is 20 milligrams. So this came from the half-life being 30 years. 30 years put in place of this formula would leave us with half of the amount that we started with. If we take this information and put it into this formula, the only thing we won't know is k, which means we can solve for it. We know that 20 is equal to 40 times e to the, I'll put 30k. First, I'll divide both sides by 40, which gives me 0.5 is equal to e to the 30k. And to solve for k, I'm going to take the natural log of both sides. And the reason for that is the natural log and e are inverses. It'll leave me with 30k. To solve for k, I'm going to divide 30 to this side of the equation, and I'll write that k is equal to the natural log of 0.5 divided by 30. I now have my completed formula. P is equal to 40, the initial amount, times e to the, and I'll write this as the natural log of 0.5 times t over 30. The same thing as k times t. Now, that's not the final answer. What we want to know is, what value of t would I put here so my answer is going to be 1 milligram? To solve this, I'll put 1 in place of p, and the only thing that we don't know is the value of t, which makes this a true statement. The process will be really similar to what we did here. I'll divide both sides by 40, so I get a 40th is equal to e to the natural log of 0.5 t all over 30. And I'm going to take the natural log of both sides. The reason being, again, the natural log and e are inverses. They cancel to give us this entire exponent. We now have that the natural log of 1 over 40 is equal to the natural log of 0.5 times t over 30. To solve for t, I will multiply 30 to this side of the equation and then divide both sides by the natural log of 0.5. I'm going to do this in a single step. T is equal to 30 times the natural log of 1 over 40. Again, that came from this gets multiplied here. To get rid of this, I will divide it to the other side, which puts it in the denominator of this thing. That is divided by the natural log of 0.5. And this is years. I don't have a calculator, so I can't estimate it, but it takes this many years to reduce a 40 milligram sample down to a single milligram.